So welcome everyone, and good morning to our North American attendees, and good afternoon to our audience in Europe. My name is Lotta Collard, and I'm the CEO of Key Performance. For those of you who don't know, Key Performance offers expert coaching and training in model-based systems engineering, in agile project management, in Lean Six Sigma, and business process management. And we're also a value-added reseller of No Magic and Katia Magic in both North America and in Europe. Thank you all for joining us today in this webinar where we will learn about and discuss the adoption of model-based systems engineering from a practical perspective. Our speaker today is Dr. Mark Blackburn, who is a senior research scientist with the Stevens Institute of Technology, as well as the subject matter expert and senior advisor with us here at Key Performance. Before I hand it over to Dr. Blackburn, I want to inform you of our format today. We will listen to Dr. Blackburn's presentation, which will take about 35 to 40 minutes. And then during the presentation and afterwards, you are welcome to type in any questions you may have for Dr. Blackburn in the Q&A. And then we will have 15 to 20 minutes at the end where Dr. Blackburn will be able to answer your questions. So without any further ado, I will stop sharing and hand it over to Dr. Blackburn.
Okay, thank you, Dr. Collard. Can you see my screen fine?
Yes, it looks good.
Okay, great. All right, thanks everybody for joining. And yes, as we're going to talk a little bit about the adoption of model-based systems engineering. It's been adopted by a lot of organizations, and I think that we've reached this time where I think that a lot of other people are very interested in. So that's what we're going to try to talk about today. So covering this sort of like the way I normally cover a course, talking about what you should expect to understand when you're finished with this. And what we are doing is that we're recognizing that our audience might actually have significant expertise in the area, and others may not actually have so much expertise. So we're going to really start from the fundamentals, talk about the key things that are related to models and modeling, and that is abstraction, the use of a precise language, and we'll be introducing and talking a little bit about the system modeling language called SysML, and how automation is enabled by that precise language. We will talk about the different types of models and their relationships. And then we will point out how model-based systems engineering and model-based engineering are different, but also need to be integrated and where the integration point is. And then we're going to use two use cases. One, a simple one that we've used in a course that we've developed. It's called a cyber physical system, which is a combination of hardware, software, mechanical kinds of things. Help this whole hopefully clarify the differences between model-based systems engineering and model-based engineering. And then finally, we're going to close out with an exemplar that we actually have, which is referred to as Skyzer, which is something we've developed as a surrogate pilot to describe various types of model-based systems engineering that actually link into models at the discipline-specific area, which would be MBE. So why do we model? Well, my friend Dr. Rob Cloutier had this chart, and I think it's appropriate, which is that we model to reason about the problem and to communicate with others. And for anybody that actually starts using modeling, and you can even think about it just even when you start trying to document something, say from an analysis point of view, even in a spreadsheet. A spreadsheet can be like a model. So in other words, you think about the columns, the kinds of information that you're collecting that are related together, and then the rows, the different kinds of things. So even in doing that, if you've ever created a spreadsheet, you can think about that the act of doing it actually helps you think about the problem. All right, so again, coming back, the fundamental concepts are these three: abstraction, precise languages, they have a formal syntax, and that is that the language is formal, and they have formal semantics, which means the meaning of what you're trying to say is also rigorous. And they include both graphical notations as well as textual notations. And because of the precision of the language, this enables automation. We'll have a couple of ways that it could be automated. So starting from the most basic kind of an example from an abstraction point of view, you've probably all seen a mobile before in your life. And so notice that a mobile, in this particular case, it shows the number of planets. It might show their relative position, but it clearly does not show their size. And so as an alternative view, which we often need numbers of different views, from an abstraction point of view, you can see here, this is a view that doesn't show anything about where the planets are, okay, but it actually shows their size. So from the sun to Jupiter down to Earth. And so we go to a famous saying from George Box, and he said, essentially all models are wrong, but some models are useful. So hopefully we're gonna be talking about some useful models here. All right, so now when we think about what we're trying to do, usually we first want to understand the operational perspective. What are we trying to do to perform some kind of a mission or to accomplish some objectives? And then the next part is, okay, well, what would the system be? And that's called the system architecture that we want to build and verify. And so then systems engineering obviously has to address these kinds of things. And again, we're building ever larger systems these days. So these kinds of technical things that we would do has to be related to other kinds of discipline-specific things. And that could even bring in things such as what we refer to as stakeholder analysis models, such as cost, or cyber, or say reliability, or risk. And they need to be able to link to these technical models. And this is an important point here, is that right now that we're getting more technical models, we realize that there's going to be a lot of subject matter experts that are interested in actually reading and looking at those models, say, for example, cost. And it's going to be very critical for us to go forward with being able to provide different ways for the subject matter experts to interact with these models, because in some ways we won't need to actually, or we won't be using documents as the primary means anymore. We'll be actually working directly in the models. So part of what I'm going to talk about a little bit today is how the tools, the enabling technologies, now allow subject matter experts to also begin to actually look and review and make edits to these particular models. And so again, so there's a lot of different kinds of other factors like reliability, maintainability, even safety, that we need to actually factor in with these technical models that were traditionally done by systems engineers. And so when we look at the roles of a systems engineer and model-based systems engineer, we need to factor in not just the requirements. A lot of people think, oh, all we need to do is worry about the requirements, but that's not the case. We now need to understand the structure, which we'll do through analysis, the behaviors, and the performance, and then we will be able to derive requirements and their associated interfaces that get allocated all the way down through different abstraction levels, down to subsystem and component levels that will be discipline specific. Again, I'm going to hit on these as we continue to go through again. Re-rendering that sort of textual description here, again, the relevant abstractions for models will be structure. These will include things like blocks, parts, which are below the blocks, properties, which is like weight or speed or different kinds of things. They're interfaces. And then we'll also look at behaviors. There's various types of behaviors that describe the functionality. We will also be interested in timing and interaction, which is generally referred to as concurrency. And we also may factor in the different kind of resources that would be related to the environment, such as are we concerned with, say, like wind or humidity, and in certain situations for the kinds of systems that we're dealing with, it might actually factor in. Then we are looking at different kinds of automation. These are generally referred to as tools. And they actually help us manage complexity and change. And yes, change management and configuration management is part of the things that will have to be understood going forward here, even for subject matter experts. So we also want to be able to generate documents directly from the models and other artifacts to check and validate the interrelationships between these views, and then combine the different kinds of abstractions for actually producing the system correctly. And we've come a long ways in the maturing of the actual tools. So many of those kind of things can actually happen. So again, these these tools are the enablers for engineering. And again, they formalize the model information, as I talked about, structural information, architectural elements, parts, interfaces, connections, behavioral information, and the system properties and constraints. And we're going to show some pictures in a few minutes to actually bring this home, because these are actually very important things that are beyond process, but what we're going to refer to as model-based artifacts. And so once we formalize those artifacts, the tools can help us analyze, transform, trace, and simulate information, as well as synthesize other kinds of things, such as the actual code, maybe test, documentation, and reports. And that's going to be very valuable as we move forward, not only for the technical expert, but definitely for the subject matter experts that won't necessarily be trying to navigate the actual models themselves. So now I've talked about the different abstraction levels. So this is, a stack of the abstraction levels. Now over here to the left, you can see I have what I refer to as model-based engineering, these tools and languages, and they're at the component level that might be, say, discipline specific, such as mechanical, electrical, software. And I'll give some examples with our Roomba example here. But then as we go up, there might be subsystem kind of models that are actually combinations of component types also. Then where model-based systems engineering is really at a level above it. So I would say that model-based engineering kind of tools and simulation may have been around already for 40 or 50 years. And maybe originally people would only talked about model-based engineering tools. But of late, I would say in the past 10 to 15 years or more, we've been trying to distinguish what model-based systems engineering is from model-based engineering. And the model-based systems engineering is dealing with helping us describe, say, the mission kind of models, which include systems of system representations, down to the system model. And you can see I drew a line right here between the system model. So the system model and all systems engineering, there's always this kind of characterization of the system architecture, and it could include functional and logical, okay, which means that you're not trying to make the specific decisions of how it's going to be physically laid out. And in today's world, a lot of the the Defense Department and organizations of that nature are beginning to actually build these kind of models, and they will stop at that point and actually provide, as the request for proposal, the mission and system models, and then they will actually have the contractors do the second part of the system model, which is looking at the physical allocations, which is also part of a model-based system engineering process, where they actually are figuring out how they're going to make their design that will respond to that process. So I'm going to talk a little bit more about this in different views in a few minutes. So what are the things that are going on? Well, traditionally, we were so focused a lot on process. And so process does describe the logical sequence of tasks, providing us some guidance on what we're trying to do. So the process actually defines what, okay, is to be done, but doesn't say how. When we look at the methods and we add specific kinds of artifacts, okay, which can be enabled by the tools, we're going to talk about the how. How are we going to represent this? And that's the rigor that we're beginning to ask for. We want to go beyond just the processes and have the how. And there's reasons, and I'll talk about in a minute. So the particular tools are enablers for describing the how, and especially in the context of things like the systems modeling language of SysML again. And so so methodologies are more generally referred to as the collection of the related process methods and tools. So here's our example that we're going to use. Probably a lot of you understand the Roomba vacuum cleaner. So there's a Create 2 platform made by the Roomba company. In here, we actually see that there's actually two systems. There's the charging station and there's the Roomba itself. And so we're going to use this as a way to describe examples about what MBE is. And so from a mission point of view, there's two things here. Clearly it cleans, but it also can return to the charging station. So going through that again, so operationally, we generally refer to what the operations are as a mission, but in more of the business context, it's sometimes referred to as a stakeholder use case. Either is fine. And so the mission, can be completed using one or more systems, as we've seen there. And so again, there's two missions. One is to clean and one is to actually charge. And the charger is really a simple system again. It has a base, which is mechanical. And these are where I want to point out what is MBE and why it's MBE. So we can see that the charger works together, but it has, again, a mechanical base, which is discipline specific. Power adapter is electrical. and transmitter is also electrical, okay? When we look at the Roomba, it has the outer shell and other components, and those are sometimes referred to as subsystems if they too are composed of other parts, okay? So the Roomba has wheels that are propelled by a motor, and now notice the motor has really both mechanical and electrical, okay? So therefore it's a subsystem. Battery to supply the power. It too is really mechanical and electrical. Got power switches to set the cleaning modes, which are electrical and mechanical, and to communicate with software that communicates with the electrical systems to control the wheels. So again, you're beginning to see why model-based systems engineering is important, is because we're going to describe the relationships between all of these things that might have been model-based engineering. And then lastly, then we have like a front bumper, which is mechanical, that interfaces, with switches or electrical to change directions if it hits an object. And so we used this for a particular course that we've developed, and I was going to go into this a little bit because we refer to this in another language. This model will be available to actually look at. It wasn't developed with the same method that was used, and it's generally deep dive. But again, engineers I know like to actually learn from examples. So I'm going to go through a little bit of this to help explain what's going on. So what we did is we have a 4-course series. The first course is about understanding stakeholder requirements. Okay, in other words, what's the concept of operation and why does it apply to a business? Okay, the second one is to look at the functional and logical nature of the architecture, very much like what would actually happen, say, in the DoD space, where they're not going to tell the contractor exactly what to build. And then at the third phase, and this is the course that I teach, which is to finish off the design and actually bring everything to life with integration, implementation, test, and that includes all kinds of verifications, unit integration, system kind of tests. And we also bring in analysis, which is called hazard analysis, which we can also do in there, which is describing different kinds of potential mishaps that could occur, such as running into a human and hurting someone. So we factor that in. And then as an example, one of the things I typically do is to Skype into it and drive it as a final test. So now, some of the enabling concepts are, we have a descriptive modeling language, again, using SysML. We have used the Open MBE, it's an open source system that was actually open source by NASA JPL. It's been around for quite a while, but it also has what's called a view editor, which is a web app. So with the view editor, with OpenMBE, you can use a tool, a capability called DocGen, which is a plugin that goes into the different authoring tools, and it'll generate the view for the information within the model, and those views can be tailored to specific stakeholder needs. It also has a model management system. So yes, model management was a key thing that they added because, and I use the word model management as opposed to configuration management, because with model management, why they actually created it is that in the years in the past, before they started it, the configuration management was not at a fine level of granularity. We want to be able to look and actually keep track of changes all the way down to, say, whatever the cruise speed is. And so I'll give an example on that one. But again, this is another concept that is not covered in this course, but it's going to be important, and stakeholders that aren't modelers will still need to understand a little bit about model management. So then, and then model-based systems engineering also allows us to go from processes to methods, which are supported by the artifacts that are produced within the tools. And then another really important capability to establish what we refer to as an authoritative source of truth. And I'll give a picture that explains what do I mean about authoritative versus, say, a single source of truth. It's called project uses mechanism. It allows us to link, for example, the system models to the mission models to the contractor subsystem models. And that's an important thing that you will see probably if you are looking in the future of working with the DoD, they're probably going to ask you to provide models that link into their mission and system models. And we do this at different levels of abstraction, but we also need to do this with, say, the stakeholder analysis models. And this, again, is where the subject matter experts are going to be looking in and actually looking at different parts of the model. And what we want to be able to do is to show them how you could use a view editor to actually use which is actually going to be running in a web browser to navigate through information that's generated so that they can actually find information, comment on it, and potentially even use the view editor to make comments about things that are in the models that might need to be updated or changed. So a little bit of history of technical innovations. One is that the flow chart, okay, which is actually a model, it's called an activity diagram in SysML these days, but the flow chart came out around 1920s, and notice that it takes maybe sometimes about 10 years or a generation before things are adopted. But there's been a lot of innovations that went into, say, SysML 1, which came out around 2006. And these include all these different kinds of little modeling languages and tools that really got formalized. And so that is what we're seeing here with SysML today, that yes, it's first standardized around 2006. And here we are, you know, a generation language later, and now we're finally getting the kind of adoption that we really need. And that's because the tools, I believe, have matured, and there's a growing body of people that realize that systems are just too complex to be able to actually do it just in documents anymore. So again, I'm going to go down through these levels of abstraction. Again, I'm going to step down through them as we talked about in a minute. All right, so the first one we want to talk about is the concept of operations. You know, so as I said, one of the things that, you know, for a telepresence robot is that we want to be able to have it so that the user could log in using a display or a remote connection. So we do that, you know, it's supported by Skype. So now you're seeing that we have communication, remote information. We can actually, along with the Create 2 platform, we also provide the teams with, you know, a processor board, Wi-Fi, camera, and display. The students assemble the robot, set up the network and the hardware and the software and the mechanical parts, and then they can add additional capabilities to it if they wanted it as a part of their deep dive. And that's what they did with this particular group. They added like collision avoidance and this Microsoft Kinetics as a component. And then all those interactions are modeled using MBSE and the SysML modeling tool. And they got extra credit for actually doing it all in a model, which they all did. So now here is what's called an OV1 or an overview model, which is of the ConOps. So it really shows that you actually have the telebug system and all the different actors and other related systems. So that's sort of like a concept of operation. You could describe it in, say, a PowerPoint diagram or other kinds of things, and actually capture that in a package as just an image inside your model. That would be fine. We also used the Unity gaming engine as a way to describe dynamic ConOps too. Then you want to actually, the next part of the method that you would do coming top down is to look at what the system domain is. And so you can begin to see the different actors that are actually involved relative to the system, as well as the other related systems that might exist in the domain. Then we go even farther in, and now all of a sudden we're just actually talking about just the context for the system itself. And so we can begin to see the different parts that it will have and their different actors. And we begin to capture that information as these types of properties. So there's part properties and there's value properties. We also, coming from the mission level, we will generally have a set of requirements, which might have a set of constraints that are associated with, say, mission objectives, but we will also have use case diagrams that actually talk about the different kind of actions. And we will normally use these actions to refine it into the behaviors of the actual systems. Another thing that I like to show is that while we have in the past used requirement management tools, such as doors and other kinds of things, I think that it's like we will actually increasingly see these requirement blocks as being embedded within the model. And it's done that way so that the actual requirements are associated with the different kinds of blocks of information. All right, so the next thing is, let me go into what we actually have here. So for SysML, it's broken into languages and constructs that support structure and behavior that actually might actually have additional constraints associated with it, which is defined in parametrics. And then from all that information, we go from one level of requirements to the next. And so therefore the requirements in effect, they come last as part of the analysis. And I will actually show that here. All right, so just mostly don't worry about the icons so much. Just think about what I'm talking about. So the first is the high level of requirements. Okay, now it could be formalized as requirement blocks. And again, you heard I prefer that. We also have what's called use cases, okay, which we've just shown. And now what we do is we start our analysis process. So we could start by looking at the blocks and the parts. We could also look at the parts and their interfaces. But in general, what we're probably going to do is do it more iteratively. So in other words, we're going to also refine each one of these use cases behaviorally. And there's at least 3 different ways to do that. There's an activity diagram, which describes the control flow and data flow. And so with the data flow, that would help inform us about what actually the interface might be between some of the parts. We could also refine a use case as a sequence diagram that's useful for things like communication or software. We could also refine a use case as a state machine. So for example, the whole UAV itself could actually have a state machine saying that it starts out in the hangar, it gets moved out to take off, it takes off, flies around, does its mission, comes back, goes to maintenance, and then goes back into the hangar. So that's different kinds of other kinds of behavior that can be described. We also have the ability to describe specific kinds of constraints. So for some of the models, there are constraint solvers that will actually work with Cameo or now CATIA Magic. It used to be called the Cameo Simulation Toolkit. But in reality, we're probably going to want something a little more sophisticated. And I'll hit on that in a second here. Now, notice also that all these behaviors, they provide us a baseline for understanding the different kinds of tests that we need to actually cover, and they would allow us to support determining the tests during execution of those tests. So this is one way that all these behaviors are things that will allow you to quantify the amount of verification effort that might be needed early on. All right, so now let's go back to the parametrics. So in reality, as I said, you could describe these constraints directly in the model. But what's really going to happen is that you're probably going to need to use other kinds of solvers. And this is where the discipline-specific or multi-physics kinds of things begin to come through. All right, so let me give you an example of a scenario here of like why we want to do this iteratively. So there's, let's suppose that the UAV had to have a cruise speed from the mission requirements of 180 knots, okay? And you're going to see in a minute here that it also potentially has to hit the deck of a ship at a rate of 25 feet per second. All right, so now if I go over and I use what's called computational fluid dynamics, which allows me to understand the aerodynamics of an aircraft, I might determine that if I put in an electrical landing gear, that I can actually achieve my 180 knots, which is my mission key performance parameter. But then with the electrical landing gear, I use my finite element analysis, and I realize that structurally the vehicle can't actually handle hitting the deck at 25 feet per second. So there's 2 different requirements that require 2 different kinds of analysis. But when I put them together, I realize that I actually need to go back and change the landing gear. So I changed the landing gear to be a hydraulic landing gear, which adds additional structure, but also adds additional weight. And when I rerun my computational fluid dynamics, I find out that my max cruise speed is now only 170 knots. Okay, so that's what a value property is, cruise speed. And now I know the value of it is 170 knots. So now the next thing I can do is, besides doing the ilities, which I talked about is modeling fault trees, now I actually have the value properties that will allow me to actually add a new shall statement that says the UAV shall have a cruise speed of 170 knots. And now what I can do is I can create my traceability all the way back to my mission requirements. And so that is how we use different kinds of artifacts that formalize the process into understanding that there's analysis that goes on before we come up with a next level of refined requirements. And so if we were going to hand these requirements off to a contractor, we can also give them all the analysis so that they can actually have a better understanding of how we got to those particular requirements. And if there is an issue, they can actually see the details of the analysis. That is what model-based systems engineering brings to bear. And that's why I'm saying that it's more than just requirements. How do you organize your model? You can do it in many different ways, but it's like, this will normally be inside the model. It's really always great to have it being one of your overview pages. And then you can also put hyperlinks in there to navigate to different parts of the model. there's no one way that's best. You can describe it this way, which is, and I said it's recursive. In other words, it has the same kinds of things: analysis, requirement, behavior, structure at every single level. Can actually have additional specialized folders or packages. We can also align the actual the structure of the model with the actual architecture of the actual system, for example. This is also referred to as the containment tree. And so this is the reason why what we really want to do is we want to be able to automatically generate views from the information in this model, because it's generally like it's going to be very difficult, mostly for subject matter experts, to navigate this containment tree. Okay, and so that is what we refer to as the containment tree. So what we want to be able to do is to expose information from the information in here that allows with a structural representation that the actual subject matter experts want to see. And that's covered in a different course. It won't be covered today, but I just want to actually give a little bit of heads up on it. So the Geyser was developed with what's called the Navigator Systems Engineering method. And that particular method, it extends the object-oriented systems engineering method, which is another standard. It incorporates a number of other kinds of good practices that come from other things, like an ISO standard for systems engineering called 15288, and other kinds of methodology guidance from other subject matter experts. And so it defines all these process steps in an activity diagram, but it also specifies the specific artifacts that should be produced. All right, so I'm going to hit on that one just a second. So what have I really covered here in some ways? Well, I'm aligning what I'm covering here with what's called the digital engineering strategies. These are goals of being able to have tech innovation, number 3, being able to have a collaborative environment, being able to have a collaborative environment with an authoritative source of truth to support decision-making and actually support workforce development. So SysML, again, came around in around 2006. So that's why it's outside the current state line right here. But the things we've actually covered is the use of OpenMBE to support a collaborative environment and for an authoritative source of truth to support decision-making. We also went from processes to methods, and another topic of interest that we're going to talk about is digital sign-offs. This is the way that we're going to be able to put sign-offs directly into the model. Again, it's another topic that's not covered here, but we'll cover it in the future. Another difficult one is how do we actually link the descriptive models that we're building, say, at the MBSE level with MBE? That is actually a challenging problem. And so there's while tool-to-tool integration is nice, it sometimes is a little brother. It's not always working. So for our other research, again, which I'm not going to cover too much here, we've used some other approaches to using semantic technology or semantic web technology to support a means to interoperate between various different kinds of tools, as well as at different levels of abstraction. And so that's what we refer to as semantic integration. These representations in these graph structures are also, like a graph database, if you will, are also really useful for allowing us to leverage artificial intelligence, machine learning, and actually mapping that kind of information to, say, digital threads, which is, you got other topics. So this slide, it effectively repeats a little bit about what was the other one. If you're going to get these slides, it'll be helpful to have the words. So again, MBSE strengthens systems engineering. Again, it helps us represent the structure and behavior, interfaces, and then the requirements. It can work at different levels of abstraction, and it actually allows us to generate different views that are relative to different stakeholders. It formalizes the information into authoritative source of truth. I'll give you a picture of that one in just a second here. And then that actually allows us to interoperate and actually communicate across the different kind of computational mechanisms, and again, supports decision-making. And this use case is actually representative of our requirement, and it's going to be available as part of the Sonic courses that Key Performance is offering. Right, so what was Geyser? So Geyser was this UAV that was created, and our sponsor wanted it to fly, fast, so that we would bring in multi-physics kinds of things to land on the ship. And we did 3 phases, one about multi-physics, one about airworthiness, which is how to get a flight clearance. Now, this is where we begin to bring in subject matter expertise, and this is why I bring this chart up. And then the last one, cost modeling. And they did that because they felt that if you didn't add cost modeling to the problem, the program managers or project managers that are actually dealing with the cost would not be engaged to actually work in here. So I'm going to hit a little bit on these in a minute too. So almost in summary of all the things I've sort of shown before I show the one particular picture is that what we've been able to do is to go and actually include systems engineering models along with these discipline-specific models that can address very specialized different kinds of analysis, as I had mentioned, by computational fluid dynamics and finite element analysis. And that's what we're trying to do. We're trying to bring all these things together. So what is an authoritative source of truth? All right, so here is a real representation. This is also publicly available. It's public domain now. And we had a Skyzer mission model. We had a launch recovery system on the ship, and we had this Skyzer system model. And notice that it's got this project uses link. So in other words, the launch recovery system looks at the mission model, just as the Skyzer does. And the contractor model actually links into the system model, and then we'll actually link into other discipline-specific models. So that's what we refer as the full stack of technical models. We used the NAVSEM method to actually build this. Okay, so NAVSEM is a kind of a reference model. A reference model, there's at least 3 types of them. NAVSEM is a process reference model, but it also, because it describes the artifacts, is a little richer. There's other kinds of stakeholder analysis models, such as, say, test and evaluation, or airworthiness, or cost. And so, for example, the cost model here is based on a military standard, at least the way we worked it, was called Mil Standard 881E. It's basically, it's the superset of all things that could actually be related to cost, okay? So it includes things such as, say, a ground system, as well as the air vehicle. So we create a specific instance of the cost model because we're only trying to talk about cost of the things that are in the full stack of models. Okay, but perhaps other kinds of things too. So let's go back to our scenario. So let's suppose that the folks in the launch recovery system said, gee, I think we should make a change over here. And if we make that change, then it'll actually change this particular constraint over in the mission model. So then when we look at that from the Skyzer system point of view, because we can actually see all that information, we say, oh, wow, I think that means that we need another verification criteria. And that means that, oh, I need another physical test. But because now the cost model is linked to these other models, we can see that, oh, wow, I can understand the cost of that potential change. We're going to say, well, let's stick with what we actually had and not make the change. So these are the kind of things that you can begin to think about. And that's an example of why being all linked together is so critically important. And so again, these models have been built in that particular way. All right, so then there's another kind of a reference model. And these used to be referred to probably more as reference architects. I like to use the word reference model because I think about this as being a generalization of prior systems. So in other words, if I had, say, a UAV, I could actually start my Skyzer model with something that was already existing out there. And it might be, say, a 60% start. And so therefore, it can really jump start where you're going. So this is really reflective of having organizations do a lot of knowledge management and curation of things that they have produced in the past to actually be able to more quickly accelerate. But I like to call these models as opposed to just architectures because they actually carry along other kinds of stuff. They have best practices, but they also may carry along verification information. So therefore, it gets you through your testing process much more quickly. Notice that I also say that there's reference models, and that's because we've distinguished systems versus missions. So in other words, we might have different kinds of mission reference models, say for search and rescue and things of that nature. So these are also very important things to think about from your organization point of view, because you'll be able to build things more quickly. And these things are probably done in a way where they've already been verified. So therefore, they're going to be probably more defect free. All right, so backing this up, let's hit on these one more time. This is sort of like recapping. So if I'm thinking about what we have here, for MBE, it's the electrical models or the mechanical models or software, but it could also be discipline-specific stuff, say network modeling. That's a custom type of thing. And then MBSE is generally referred to as descriptive models as opposed to discipline-specific models. And they describe those logical relationships. They describe the parts and properties of the actual system. Model-based systems engineering might also be an abstraction or use the abstractions for an MBE. So in other words, an MBE model might look like a block inside of an MBSE model. And so then also those descriptive models, they represent the interconnections of the parts, the functions, and they also can actually reflect the behaviors that need to be tested to verify things against the system requirements. And again, these descriptive models, they can be both functional and physical. And for a large scale corporation, a business oriented group, you probably would actually have both. Right now, these words are in here so that you can understand the story that I'm going to tell in a minute. So let me just go to the story. Okay, so here's the problem. It's like, I want to try the value proposition for why we want to actually adopt MBE, MBSE, but let's look at it from an example of why we would never go back for model-based engineering. All right, so here we are. I've been in a place where they actually had these Mylar drawings of what they kept before they actually had CAD tools. And the scenario is, and this is a true story, is that the exhaust manifold was put too close to the electrical components, and what happened is that the heat radiated and actually caused a defect later on after the system was already built, right? So if you're going to go and fix that problem, what are you going to do? Well, you're going to find the old Mylar in some cabinet, come out of here, put it on your table, and then redo the calculations to try to figure out how to relay it out. That is completely different than where we're going to do it today. So first is like, we would actually be able to use our model management system, find it exactly, okay, make the change. But here's the thing, we probably wouldn't have actually gotten that problem because we're probably going to use our reference architecture of our heat radiation libraries in the design process. So therefore we design it. So therefore we know that the electrical system is not too close to any kind of thing radiating the heat. So that's sort of like the value proposition. We would never go back to using Mylar, and that's exactly where we are right now. Why should we ever go back to actually just using documents when we have all this evidence about how we can actually do model-based systems engineering and integrate it with model-based engineering for the future? All right, so in summary, it's so modeling for both MBE, SE, and MBE, it helps us use different modeling language, abstractions to basically manage this complexity and change. It leverages a precise language, enabling automation. We need to actually determine how the model-based technology objectives might be applicable to our organization. And sometimes if you're just doing this for the first time, you might want to consider a pilot where it doesn't have so much risk, but you want to look at your particular processes. No need to potentially not actually use a number of them that are out there. There's some out there that are quite good already. You can look at how and what, okay. Also, you need to think about the modularization. As you saw, the layers that we actually have for mission, system, subsystem, you need to actually have a methodological approach to that modularization too. And that will actually factor directly into model or configuration management practices. I highly encourage leveraging the technologies such as project uses because it is a way to integrate the descriptive models to support modularity, access control, which I didn't even talk about, and reuse. And then the model integration across these disciplines, is more challenging, and we have other examples to talk about that too, but that's for another talk. And I say thank you very much for your time today.
Thank you, Dr. Blackburn. That was very interesting. And for all the people in the audience, I want to let you know that we have recorded this webinar, and we will provide you with a recording that will be available to all of you. So you can go through it at your own pace later and use it as a reference as well. So you're welcome to type in questions in the Q&A now that I can ask Dr. Blackburn. And we already have some questions that have come in. So the first question is, I understand how systems engineers adopt this method, but how do we get the consumers of the models to embrace the new technology?
Yes, that is a good one. That's sort of like the one that I've been talking about. That is, I suppose, the biggest challenge. I can tell you the way that we did it for this. All right, is that and I guess it does matter about the people, but when we were working with the Navy, they actually had they knew that they wanted to go from like the document-based kinds of things, and they had a very elaborate cost spreadsheet. But again, it would be the traditional process would be to do clone and go. In other words, find a program that was like before, clone it, and then continue to move forward. But they realized that probably wasn't going to work now that we had all this other kinds of stuff. So we had a subject matter expert that had been doing cost modeling for many years, and they teamed him up with some young engineers who actually supported making the models. And so that's the way I would say that it'll happen in the future. And honestly, I think it was a continuous process. The way we did it is, I suppose this is very agile in the way Lota would actually talk about things, which is we just continuously met every single week as we moved through and actually began to continuously incorporate all of the different kinds of methodological approaches into the reference model, as well as building a specific example. This is why these pilots are very useful, because they teach people through examples, and a lot of people like things through examples. The other thing, and I haven't gone into what the DocGen did, but also in both the cases for the airworthiness model and the cost model, we let the subject matter expert who understood what information they wanted to get out define the actual template that is used by DocGen to produce the documentation that they're used to seeing. So there's many different things, and that is definitely something that we would like to actually have another talk on. So hopefully they answer that question.
And we are developing a course for modeling use for non-modelers right now. Right, Dr. Blackburn?
Yes, yeah.
And so next question. What is the process for continuous improvement in SysML?
Well, here, I would say that it's like the continuous improvement in some ways has been actually addressed by other people that were the early adopters. Because I can imagine if you would start out with, say, the NAVSIM model process or OOSE, I would say that it's like they were the ones that actually figured out how to do it. And so the only thing that I would say that would be different is that if you took these modeling methods and tailored them, then you basically are dealing with continuous improvement. Again, remember, we have those models and they are formalized in this way. So in other words, we have an activity diagram. It's a model, okay? And again, this NAVSIM model is a model, and it also is publicly available. I mean, you might have to ask NavAir, but it's like, it actually details out all the process steps. So if you were going to go through continuous improvement, I would say your continuous improvement would be one of tailoring this particular process model or this reference model.
Okay, thank you. Next question. SysML version 2 is a very large modification of the original that has raised both hopes and concerns. What is your view of SysML version 2?
I really can't wait to get it. It's like there's so many things about SysML v2 that are so great. One is so how, okay, let me go first. It's like, so how do we, and I don't even have that chart up here, but it's related to this semantic technology. One is that SysML v2 is supposed to output information that is going to be related to semantic web technology. That's a particular language set that might be referred to as ontologies versus from OWL2, with the actual data being what's called the RDF or resource description format. And it's like framework. And then if you do that, we could potentially round trip between going through tools that understand semantic technology information and going back to descriptive modeling tools. The second thing is that it actually has a formal syntax. And so one of the challenges that we actually have, say now, is like if you actually are using, say, this is a pretty technical answer I know about, but I'm just going to give it to you anyways. But it's the if you're actually going to create something, say you wanted to have a subject matter expert create a new object, okay, as they actually are reviewing their model, they can't necessarily do that. You'd have to go in with the modeler because there's a specific unique ID that's created in the SysML authoring tool. Well, the potential for actually getting around that is great because you can create stuff directly in a like an environment that actually can read SysML language from a syntax point of view. And a lot of the actual graphical things are actually rendered automatically. So in other words, you don't necessarily have to sit there with a graphics tool to do a lot of things. And there's a lot of things that can be more efficiently done just from a language point of view. So I could go on a long time on why this is, I think, going to be really, I mean, besides the language itself, how it aligns much more with the way that we would build a model for, I know it's called an ontology, which is a set of classes of information. Yeah, I really like it a lot. I can't wait to actually use it.
Okay, thank you. Next question. In your SKYSER example, were all the models, such as cost, system, and mission, in the same tool, or was there integration between different tools?
Okay, for SKYSER, all of these were in the same tool. All these parts down to the even actually what we did with some of the stuff, we did use MATLAB for some of the landing gear stuff, and that would be an integration that you would see, but all of these were all in the same tool. They're all descriptive modeling languages, all done in Cameo or Magic Draw, which is now Contia's, I guess, Magic System of Systems.
Okay. Now, would you recommend developing reference models using the same modeling language as the one used for design, such as SysML, or a meta language at a higher abstraction level, such as UML?
Okay, now I would use, yes, these reference models, they should be in the same languages, because what you're going to do is you're going to create an instance of this. And so, yes, make these the same as what you're using here. So these are all SysML. We're not trying to actually create I think the question is almost like creating a meta model, okay? And I realized that it's like, for example, SysML v2, there's a meta language called kernel that is actually being used to describe it. So I don't look at those reference models as being a meta model like kernel. I look at it as just really being a superset of all things that would be described here. Same thing also with these reference models. These reference models are really generalizations of prior systems over here. So they definitely make sense to actually have it being the base thing, because they could instantiate it as a model over here and then tailor it as you go forward.
Okay, thank you. And we should add there that the SKYSER model is incorporated in our classes that we offer online. Next question. I have worked with introducing MDD at large companies for 25 plus years, and all I can say is it's difficult. What about automation for generating the final code in the slides presented today?
Okay, so for okay, so I know what you're talking about, but that's much more say probably discipline specific, where you're dealing with UML. And trust me, so some of this information I did in presentations all the way back in 2008. So I sort of have been like an evangelist for a long time, and I do understand what you're talking about in terms of the challenge. But again, for the descriptive modeling things here, this is not going to manifest itself in code. Okay, I'm sure that where you were model-driven development was probably when you were really dealing with it from a UML point of view. And there was also challenges in trying to use UML. And I remember those days about people trying to round trip using different tools where it was only generating part of the code, more of the classes and the method structure than all the details.
Okay.
But I agree with that.
Okay, we have time for maybe one or two more questions.
Okay.
So in the SKYSER example you discussed, when the change was proposed that led to understanding the cost and system impacts, were those linkages originally built into the model to answer that type of question, or were the models built and later found to be useful to answer that type of question?
We basically probably built it to basically illustrate that kind of question. So SKYSER is not a complete system. SKYSER is a set of deep dives to exercise and show different examples that are related to all this kind of thing. So it's not a real system. It's really a unclassified system for workforce development.
Okay, and one more question. With automation, I mean transferring UML2 models to code. According to Brand Select 2 weeks ago, the SysML2 is a whole new language, new meta model, not based on UML2 profiles. Do you have any comments on that?
I agree with that. So, and I do know Brand too. And actually, Object Time was one of the better automatic code generation tools that actually occurred. So Object Time was actually one where Brad Selleck actually had a lot of influence in before he went to IBM. So yes, I know it is completely different, and that's actually one of the benefits. So it turns out SysML v1 was built by extending UML, and SysML v2 is not. It is going to be its own thing.
Okay, so now I'm gonna ask you to stop sharing, Mark. And I will share some upcoming events before we let you go. We have the Cyber Symposium in Gothenburg, Sweden, coming up on October 11 and 12. And then on October 26, we have the virtual CO, which will have 5 presenters on MBSE. CO is it's for the user groups. And if you are interested in any of these, please let us know. And we will send you a recording of this webinar. And we will keep in contact with you if you need more training or more help, or if you're interested in another webinar that will be coming up with Mark Blackburn. Thank you all for attending, and have a great day.